Hey viewers, let's continue from the video yesterday. We're going to learn a fundamental but useful tool in number theory called the modular arithmetic. So before I explain what modular arithmetic is, we're going to learn the definition of two terms. First, we have the term called the modulus. And then we have the term called modulo, or more correct way to say it is congruent modulo. So first, let's talk about what modulus is. Modulus is just saying that we're going to choose an integer, or in particular, we would like to choose a natural number. Suppose it is k. Then suppose there are two other integers, a and b. Then we will say that a is congruent to b in modulo k, and denote it this way: a congruent to b modulo k. What does this statement really mean? We say that a is congruent to b modulo k if and only if a and b has the same remainder after divided by k. Right. Modular arithmetic is just a system of arithmetic or calculation of integers, in particular to find out the calculations of the remainder parts after we divide by some integer. So in this case, we are just saying that if a divided by k, the remainder here, let's call it r sub a, is equal to the remainder of b divided by k, let's call it r sub b. Moreover, modular arithmetic is again a system of calculation of integers, and it actually inherits the arithmetic of regular calculation, such as addition, subtraction, multiplication, and even exponents. The only operations, however, which modular arithmetic is not allowed is division. So I'm going to give you some examples of each operation to see what I really mean by the similarity. So what are we going to do? Well, we can either add them together and then divide by 3 to find the remainder. In this case, we'll actually get 5 plus 2, which is 7. Then divide by 3, we end up with remainder 1. Keep that in mind. Here, in modular arithmetic, we are also allowed to do the other way around, meaning we can simplify the numbers into something a lot smaller, and then we're going to add them together and then reduce again. So in this case, we can also do that 5 divided by 3, so that we can simplify the 5 first, as 5 is greater than or equal to 3. So in this case, we end up with 1 remainder 2. So we can reduce the 5 into 2, and then we are, of course, have plus 2. Then if we add them together, we get 4. And once again, 4 is greater than 3. We can reduce it one more time to get 1 remainder 1, meaning the remainder is 1. So this matches with the calculation that we have in a normal calculation. Again, if we do the regular calculation, and first we're going to subtract, before we divide, we will end up with 14, and then you can find out that the remainder is 1 in modulo 13. If we use modular arithmetic to find out, we can reduce each one to something a lot smaller before we combine them back together. So we have 49 divided by 13 is going to give us 3 remainder 10. So we can reduce 49 into 10. Similarly, 35, we can reduce it into 2 remainder 9. So if we subtract these two numbers, we will be able to get the same remainder, 1. That checks our answer. Okay, then of course we can just take the products first, like how we usually do it, and then to divide it and find out the remainder part. If we do it that way, we will get 23 times 17 giving us 391. Then if we divide this by 19 to find out the remainder, we will end up with 20 remainder 11. So the remainder part is 11, and this is how we do it regularly. Now with modular arithmetic, again, we said we are allowed to reduce the numbers into something smaller and easier to calculate. Then we can do it in the following way. We have 7, which is less than 19, we can keep it as it is, times 23, which is greater than 19. So we can just reduce it first and find out the remainder part, which is equal to 4, because 23 divided by 19 is 1 remainder 4. Good. So if we multiply them together, we get 17 times 4, which is 68. And once again, we're going to reduce it. Then we have 68 divided by 19 is 3 remainder 11, which matches to our calculation at the beginning. In this case, we end up with 17 minus 19, which is negative 2. And again, by the definition, 17 is congruent to negative 2 in modulo 19. So they have the same remainder, meaning that in this case, these two are actually treated as the same thing, or the same value. So in this case, we will be able to do our calculation even faster. We have negative 2 times 4, which is negative 8. And once again, when we get to our answer of the remainder, we want it to be between 0 to the modulus, not modulus minus 1 actually. So since we have negative 8, which is not inside the range, we just need to add it back. So in this case, we'll add 19 and give us 11. Of course, we can just simply multiply it or take the exponent. And again, raising to some power is the same as multiply with itself that many copies. And therefore, if it works for multiplication, the exponential calculation will also work in the same way. So of course, we can just take the exponent first and then reduce it. So in this case, we'll end up with 4. So in this case, let's try to break it into 3 times 2, or 3 plus 2, excuse me. Then by regular calculation, we said we will be able to break it into 2 to the third power times 2 to the second power. And this also holds true in modular arithmetic because we're only taking the product of itself by how many times. And we just said that the multiplication, the way of multiplication works exactly the same between the two different systems. So after we break it into 2 factors, we can now try to first reduce each one. So 2 to the third power is 8, and 8 is bigger than 7. So let's reduce it. 8 divided by 7 is 1. Remainder 1. So the first term can be reduced down to just 1. And then the second term is 2 squared, which is clearly 4. So we're going to multiply by the second term, 4. Then we can now take a product to get 4, which actually matches with our first answer here. Great. We're going to consider 2 numbers, 15 and 20. Now, we are saying that 15 is actually congruent to 20 in modulus 5, right? 15 by 5, we have 3 remainder 0, so we can reduce down to 0. Similar to 20. 20 divided by 5 is 4. Remainder 0. Okay, no no fraction, no numerator part. Right. So another way of thinking of modular arithmetic is we're trying to figure out the numerator part when we take a number divided by the modulus and write it as a fraction. Okay, so they're all the same. But anyway, since we have 15 divided by 5, which gives us 3, and it's a whole number, and meaning that there's no remainder. Same for 20. These two are congruent in modulus 5. However, we're not allowed to divide by 5 in this case. Why? If we try to divide by 5, we end up with 3 and 4 respectively. But 3 and 4 are clearly not congruent in modulus 5, because if we try to take the remainder of 3 and 4, it'll be 3 and 4 themselves, but clearly 3 is not the same as 4. So in this case, these two are not congruent, even in modulus 5, and this is a reason why we're not allowed to do division. Perhaps you may ask, well, in this case we're dividing by 5, which is the same as dividing by 0 technically, because 5 is congruent to 0 in this case. So if we're trying to divide by 0, clearly we shouldn't do that, right? So if this is not convincing yet, let me give you another example. Here's what we have, such as 8 is congruent to 2 mod 6. And I believe this is obvious enough because 8 divided by 6 is 1 remainder 2. Clearly it should be congruent to 2, right? But in this case, we're not even allowed to divide by 2. Because let's say if we try to divide by 2, and let me mark it in quotes, because again, we're not supposed to do that. Here's the reason why. Suppose we divide by 2 on both sides. 8 divided by 2 is, of course, 4. And 2 divided by 2 is 1. But is 4 same as 1 in modulus 6? No. Because 4 divided by 6 has a remainder of 4 itself, and 1 divided by 6 is, of course, remainder 1. And 4 is not the same as 1. So these two are clearly not in the congruent class. Or in other words, they're not congruent. But we start off with something that's congruent, and this time we're not dividing by the modulus itself. In other words, we're not even dividing by 0 either. Why is it not going to work? Well, this actually can be explained in ring theory and in other topics of natural algebra. I'm not going to go through it in this video. Just keep in mind, because of these counterexamples, we can see that modular arithmetic is going to work similar to regular arithmetic or regular calculation, except there are a few things that are not allowed or forbidden to do, such as division and taking the roots of some power, as I just mentioned. Since we want to show that it's a multiple of 6, or 6 is something that we're going to divide by, we want to show that n cubed minus n is congruent to 0 modulus 6. So in this case, we're trying to take the modulus of 6, meaning that we're going to divide by 6. In other words, if we want to think of the incongruent classes or numbers, there are only 6 numbers in total that we need to consider of. We just need to consider 0, 1, 2, 3, 4, and 5. And again, if we keep moving on, 6 is the same as 0 in this case, 7 is going to be reduced down to 1, so on and so forth. And for the negative part, we can also do the same thing. Negative 1 is going to change it back into 5 because they have the same remainder. Negative 2 will be the same as 4. And therefore, there are only 6 different values that we actually need to think of to see if this statement is true. Then, since we now have finite amount, and in fact there are only 6, we can just simply brute force it and climb up the mountain to check each case quickly to see if we get the results that we want. So let's draw a table. We have the first term is n, and then in this expression we also have n cubed. So now we can combine them into n cubed minus n for the last row. Then of course we need to check all the possible cases: 0, 1, 2, 3, 4, and 5. Then we just need to fill in the values for each grid. We get 0 cube is 0, of course. 1 cube is 1. 2 cube is 8, which is reduced down to 2 and 1 is 6. 3 cube is 27, divided by 6 is 4 3. 4 cube is 64, divided by 6, we have 4. So here we use 4. And 5 cube is 25, divided by 6, we have 5. So now we're just going to last row. We're going to take the second row, subtract the first row. We get 0, 0, 1, 0, 2, 0, so on and so forth. Now, this one is kind of straightforward, but also will only work if there are only a finitely, well, actually small amounts. And again, this method right here will also help us to quickly check whether if we have any counterexamples or any cases that fail. So in this case, all the numbers in this list work, meaning that we can claim that n cubed minus n is always congruent to 0, no matter what n we choose, in modulus 6. Then we can finalize our conclusion and say that n cubed minus n is a multiple of 6, no matter what n is, or n is an integer. And this is how we use modular arithmetic to help us solving a number theory problem in a faster way, instead of listing all the cases out. Pretty cool, huh? So yeah, that's it. If you think the idea here actually amazed you, please share it so that you can also let other people to understand a new concept. And if you enjoyed this video, don't forget to like and subscribe my channel so that you can check out my other videos. And if you have any thoughts or ideas, please leave your comment below. I will see you guys next time.